Implication of remote sensing techniques in identification of linear features and delineation of lithotectonic units of Badrama Jamankira area of Sambalpur district, Odisha, India. Abstract: in any geological study, may it be regional or local, it is crucial to identify different rock units, trace out their areal extension and draw the boundaries as accurately as possible. Remote sensing techniques have been proven through several studies worlds over, to be a reliable tool for a large area mapping and need-based thematic analysis cum interpretation, as the satellite images have the capability of providing a synoptic view of a large region in one scene and allows to perceive the relations of different lithological units of a region. Vital geological information related to lithology, geomorphology, structure and tectonics are obtained through the visual as well as digital method of interpretation of satellite imageries. The tonal-textural variation exhibited by different rock types help scientists and researchers in identifying linear features, delineating lithotectonic unit and interpreting litho-assemblages of the area. Keywords: remote sensing, linear features, structural pattern, lithotectonic units, thematic mapping, IJERT Jamankira supercrustals, Badrama belt. Introduction. Although the classical method of geological mapping is found to be the best suitable means for precise collection of field data, but while covering a wide area for regional geological mapping in multifaceted topography somehow limits out the physical access to the target area. Also, such strenuous field practices consume unnecessary time and efforts. Under the circumstances, remote sensing technique seems to be an advantageous option for covering a widespread area of interest. Satellite-based remote sensing techniques give us such liberty to extract accurate needful geological information in terms of linear features, lineaments and structural pattern etc. from the imageries. Further, a generalized litho-assemblages boundary and lithotectonic delineation can easily be interpreted through such imageries. Accordingly, a meticulous extraction and the interpretation of the lineament need to be done. If visual extraction looks to be inaccurate, a software-driven method of lineament extraction may also be adopted. But before establishing those as final facts, a ground validation of the selected area should also be done. As stated by Katswaki et al., 1995, Moore et al., 1998, and Walsh, 2000, the extraction of linear features through satellite images may broadly be categorized into I. Lineament enhancement and lineament extraction for characterization of geologic structure. 2. Image classification to perform geologic mapping or to locate spectrally anomalous zones attributable to mineralization, Mustafa et al., 1995, Susan and Toprak 1998, and 3. Superposition of satellite images and multiple data such as geological, geochemical, and geophysical data in a geographical information system, Novak and Solakalis 2000, Simara and Gebrib 2006. As the integration of remote sensing data in actual period is supposed to be a bulk tool for extraction and interpretation of geological features, numerous researches are being conducted for precise adaptation of both passive and active remotely sensed data into instinctive detection of momentous geological features like linear features. 2. Study area. The study area Badrama Jamankira measures about 700 square kilometers, covering parts of the supercrustal rocks of IJERT Jamankira area, the western part of granulite terrain, Rangoli province, a small segment of CIC covered by a narrow strip of Gondwana rocks, and a trivial segment of Jharsuguda complex, which lies in the northern part of Sambalpur district of Odisha state, has been selected for regional geological mapping. Fig. 1. The RK lineament, which defines the northern boundary of CIC and EGMB, also passes through the area. The study area is bounded by latitudes 210.28 and 21,045 n and longitudes 840.07 and 840.21 e and covers 290 square kilometers of Survey of India topo sheet number 73C/2, 30 square kilometers of 73C/3, 350 square kilometers of 73C/6 and 30 square kilometers of 73/7 as shown in Fig. 1. 3. Resources. To get a holistic idea about the lithotectonic units and structure of the west-central part of Odisha, including the study area, multiple scenes of the space-borne multispectral images have been used. Both panchromatic images and false color composite, FCC, images have also been interpreted in course of the study to outline the prominent linear features. Lineaments and lithotectonic units. Different scene used in the present study is listed in Table 1. Fig. 1. A. India map showing the position of Odisha. B. Map of Odisha showing the location of Sambalpur district. C. Satellite image map showing the three crustal blocks, North Odisha Singh Bum Kraton, NOSC, Central Indian Craton CIC and Eastern Ghats Mobile Belt, EGMB. D. Satellite image covering the study area. 4. Procedures and interpretation. At the outset, a mosaic was prepared manually by placing the imageries side by side in such a sequential order of latitude and longitude so that the photo/image features look connected through one another. In the initial stage, visual method of interpretation was adopted, i.e., lithic units and structural features were differentiated based on observed variation in tone, color, texture, shape, size, pattern, association, vegetation cover and drainage pattern. After the imageries covering the west-central part of Odisha were placed properly, the relevant features were traced on a tracing sheet. Based on the distinct characteristics, 7 lithotectonic units were outlined, Fig. 1. 1, which are as follows. 1. Bona Granite Complex. 2. Tampercola Granite. 3. Diagur Belt. 4. Badrama Belt. 5. Kuchanda Granitic Complex. 6. Jharsuguda Granitic Complex, and 7. Sambalpur Granitic Complex. Apart from delineation of lithotectonic units, lineament analysis forms an important component of satellite image interpretation. Lineament is variously defined. In the present study, the definition of O'Leary et al., 1976, has been followed while doing interpretation and image feature extraction. According to them, a lineament is a mappable linear feature of a surface, may be simple or composite, whose parts are aligned in a rectilinear or curvilinear relationship and which differ distinctly from the adjacent features and reflects a subsurface phenomenon. Early investigators, viz., Hudson, 1974, Kutna, 1974, have separated several classes of lineaments corresponding to such structures penetrating the Earth's crust as near vertical faults, different joint patterns, shear zone, steep vertical compositional banding or planar tectonic fabric. Following their pattern of separating different types of structural elements, the following procedures have been adopted to delineate different types of lineaments existing at the regional scale, Fig. 1-2. 1. Discontinuous linear/curvilinear features have been related to deformational or compositional layering. 2. Continuous straight lineaments, curvilinear features within a specific lithological unit have been considered to represent folds, megajoints or faults. 3. Curved but continuous lineaments have been taken either to represent deformational banding on regional scale or shear zones. Image interpretation and subsequent ground validation clearly confirms that different color/tone, geomorphic features, drainage pattern provide reliable information about different rock types. Pandya, 1984. A coarse texture indicates very rugged topography, which itself hints presence of massive crystalline rocks cut across by faults and joints. In the color or the tonal variation is reflected the nature of vegetation and composition of the rocks that occupy a region. Drainage pattern provides additional information about the lithological characters because the pattern is controlled to a large extent by the competency/erodibility of the rocks and structures, viz. bedding, foliation, joints, faults, shears, etc. Granitic rocks form flat or moderately undulated terrain, and exhibit light color with little tonal variation. Such an area is characterized by dendritic drainage and occasionally rectangular or angular drainage pattern. Dark tone signs basic rocks. Metasedimentary rocks with alternate competent and incompetent lithology usually show linear and curvilinear features which run parallel to one another in close cluster. In such areas, the drainages run parallel to the hills, giving rise to parallel/subparallel drainage pattern. As the infiltration of water is more in the metasedimentary rock types, the drainage density is comparatively less than igneous/crystalline rocks. Subsequently, digital interpretation of the images which cover the study area was done. The downloaded/scanned raster images, .jpeg/.pdf, were georeferenced in desired projection system through suitable software like Global Mapper and ArcGIS. Various maps, viz. Terrain model, Fig. 1.3, ridge slope, Fig. 1.4, slope direction, Fig. 1.5, were prepared through software-aided analytical techniques. The information generated through visual and digital interpretation helped to trace the boundaries of lithotectonic blocks, identify rocks of different parentage, trace out structural features, and made the job of geological mapping much easier. Fig. 1.6. In the absence of satellite images and the modern tools and techniques of extraction of geological information, it would have been difficult to complete geological mapping of a terrain like the present one within a short time period. Unit I, Jamankira Lithotectonic Unit. The Jamankira Lithotectonic Unit is a part of Diagur Belt, covers the eastern part of the study area. This litho unit displays lot of color variation in the IRSIB, LIS 3 FCC. It also exhibits variation in texture from very coarse to fine. Linear and curvilinear features are very prominent in the central part of this unit where the texture is coarse. The linear features are less prominent and discontinuous in southern part. Field verification revealed that the areas which are thickly forested, appear brown to red, whereas the areas with poor vegetation look light gray to pink. The areas characterized by linear features were found to be occupied by well-foliated, metasedimentary, rocks, mostly coarse-grained quartzites of different color and composition. The areas having fine texture are mainly covered by granitic rocks with a thin blanket of soil at places. Drainage pattern observed within this unit varies from dendritic to parallel from place to place depending on the rock type present. It was established that the variation in color, texture, distinction of linear features and drainage pattern is the reflection of the presence of varied rock types in this unit. Unit 2, Badrama Lithotectonic Unit. To the southwest of Diagur Belt lies the Badrama Belt. This belt appears to be sinuate-shaped, and covers the central part of the study area. The outline is that of a leaf, which gets wider in the southern side and acute towards north. In the IRSIB, LIS 3 FCC this unit displays brown to deep brown color. Linear and curvilinear features are numerous and prominently developed over major parts of the area. About 110 lineaments of different lengths have also been delineated. Based upon their orientation, these lineaments have been classified. The prepared rose diagram, Fig. 1.8, suggests that statistically the NWSE, N1200 to N1300, trending lineaments are maximum in numbers in the area. In the satellite imageries, it exhibits a very coarse-grained fabric, i.e., the topography is rugged. Superimposition on topo sheet suggests this unit to cover the hill ranges like Gajuda Chinamale in the south and Sarb to Samarsinga in the north. Ushakothi Wildlife Sanctuary falls within this unit. Dendritic pattern of drainage can easily be visualized in the software-driven analytical image. Sarkar et al., 2000, stated that the area is occupied by charnokites and garnetiferous granite gneiss. During geological mapping, many more rock types like hornblende schist, garnetiferous biotite schist, calc gneiss, granite gneisses, garnetiferous granite gneisses, hornblende granite gneiss, migmatite, dolerite could be identified. Prominent foliation is the result of deformation. The variation in attitude of structural features suggests the rocks of this block have undergone multi-phase deformation. Unit 3, Katarbaga Lithotectonic Unit. Katarbaga Lithotectonic Unit lying to the west of Badrama Lithotectonic Unit is a small segment of the falcate-shaped Jharsuguda granitic complex of Nayuk, 1989. It covers only 30 square kilometers of the study area. The contact between Badrama Belt and Jharsuguda granitic complex is almost straight one and is clearly seen in the satellite images as a lineament. It is identifiable based on the tonal and textural variation of the two units. While Badrama Belt is characterized by red to dark brown color and coarse texture representing a thickly forested area with rugged topography, Jharsuguda granitic complex has light pink to gray color and fine texture in IRSIB, LIS 3, FCC, except a small area showing coarse texture with prominent linear pattern. Ground truthing revealed the area to be occupied by granitic rocks within which occur metasediments like biotite schist and quartzites. The area in the southernmost and central parts of this unit exhibiting coarse texture are occupied by curvilinear ridges and are composed of well-bedded, sheared quartzite. Unit V, Yaharmanda Lithotectonic Unit. Yaharmanda Lithotectonic Unit forms a small part of study area. It lies in the southwestern corner and is separated from the Katarbaga Lithotectonic Unit by a prominent lineament. Tonal and textural signatures indicate that the area is flat and almost free from prominent linear or curvilinear features, light pink to gray color and fine texture in IRSIB, LIS 3, FCC indicative of an area with no forest cover. These features suggest it to be occupied by much denuded granitic rocks and or soil. While ground validation the area is found to be occupied by grained porphyritic granite. V discussion. Based on the data obtained from visual and digital interpretation of satellite images, a lineaments map of the study area is prepared, Fig. 1.7. It is established from the generated data that megalineaments divide the study area into 4 blocks, each block having a characteristic rock assemblage and structural features of its own. Apart from these, numerous major and other lineaments of different lengths have also been delineated. Their orientation differs from block to block. Whereas, NWSE trending lineaments are more in Badrama and Jamankira blocks. The NS and EW trending lineaments in Katarbaga block are more. In each block the nature of the linear features, representing the bedding and foliation traces are different, suggesting rocks of different blocks were folded separately. In Badrama lithotectonic unit, lineaments are prominent but short in length, muddled and exhibit much variation in their trend. In Jamankira litho unit, lineaments are less prominent, short in length, organized and mostly remain subparallel to each other. The Katarbaga lithotectonic unit only 2 lineaments could be recognized. Acknowledgement. The present work is a part of the research work of DKT carried out under guidance of Dr. Ashutosh Nayak, Professor, Retired, Department of Earth Sciences, Sambalpur University. DKT is thankful to Dr. Nayak for his guidance while satellite image interpretation and ground validation. The authors are thankful to Director, Orsak, Bhubneshwar for providing the obligatory inputs in course of their research. Authors also thank Mr. Ahoda Sister Scientist JSAC, Ranchi for his productive recommendations during the preparation of the manuscript.